So programmers have this ritual where when we start a new program, we output hello world. But in graphics, there's a different version. This is hello triangle. And it's kind of the equivalent. It's just the minimal program that gets things up and running. So I want to write this in C. And we're going to write this program and pipe it into another program. So this run script compiles and then pipes our output into ffplay. And this is going to interpret our output as an image. So when I run it, we're outputting hello world right now, which is not a valid image. So it's complaining about that. So let's look at what it expects. We're setting a video size of 1920 by 1080. We're telling it to read raw video and pixel format RGB 24. So this means 24 bits, which is 3 bytes. So what we want to do is write 1920 times 1080 times 3 bytes to output, and then it will interpret that as an image. So let's do that. The putC function outputs 1 byte to standard out, and this number needs to be between 0 and 255. When we run this, we get a black screen, and we can change these. So I'll change the first value to 255, which gives us red. The second value gives us green, and the third value gives us blue. So we're going to keep this same basic structure, but we want to vary these colors across the screen somehow. So instead of looping over one loop, let's do 2 loops. One's going to go over X and one's going to go over Y. I'm going to define the width up here and the height. So that should have the same output. But now we could set R to X and B to Y. And then we get a pattern. So this repeats because we go 0 to 255, and then we keep increasing, but our putC function is truncating that to 1 byte. So it's taking mod 256. And so we get this pattern here. And now what we want to do is only fill in part of the screen by defining 3 corners of a triangle. So let's define one corner. We'll have an x0 and a y0. And I'm going to make these floating point numbers because we could define a triangle with subpixel coordinates. There's no problem with that. And let's just say this is width times 0.5 and height times 0.5. So first let's just fill in pixels that are on one side of a line passing through this point. So we could say that these are initialized to 0, and if x is greater than x0, we're going to set R to 255. Or actually, let's keep our same pattern, but we're going to do this. Okay, so now we're only filling in half the screen because we're checking x greater than x0. We could also check y greater than y0. And so let's define 3 points. I'm going to copy these to x1 and x2. Let's say that this is 1/8. So those should define the 3 corners. So if we look at what our x0, y0 is down here, our x1, y1 is up here, and our x2, y2 is down here. But because these are diagonal from each other, we can't just check. We can't just check against vertical and horizontal lines. We need a way to determine whether a point is on one side or another of a diagonal line. And for that, we use the determinant. So here we have 2 points, A, B, and C, D. This is the origin, 0, 0. And so this 2D determinant, AD minus BC, gives us the area of this parallelogram. But it can be positive or negative, so if I move AB over here, we get a negative area. So this is also telling us which side AB is on relative to this line. If it's positive, we're on this side, on the right side. If it's negative, we're on the left side. So let's use this to check against one of our lines. I'm going to define the determinant function. And let's take the center of a pixel. So we're going to define this Cx and Cy. When we have a grid, the top left of our screen is 0, 0, and integer pixel coordinates are at these grid lines. But if we have a triangle on the screen, we're actually interested in whether the center of a pixel falls inside the triangle. So we add 1/2 to our grid coordinates, and we test against that point. So we have our pixel center, and let's check against the line between 0 and 1. So we'll take the determinant, and if d is greater than or equal to 0, then we'll fill in a pixel. So this will be our edge. This is V0, V1, and this is the point we're testing. So we want to take V1 minus V0 for the second point, and for the first point, we'll take center minus V0. So center minus 0, and then 1 minus 0. So that actually fills in the wrong side. We would expect this side to be filled in. And that's because in this diagram we're using y going up. But in our image, y is going to be going down. So the sign is flipped. So what we can do here is just pass these in the opposite order, and that'll flip the sign. So now we're filling in one side of one edge of our triangle. So if we repeat this for the other two sides, we'll get just the points that are on the correct side of all three edges. So let's copy these. And then we're just going to go around the triangle clockwise. So it'll be 1, 2, 0, 0, 1, 2. Like that. And then if all three are greater than or equal to 0, we fill in a pixel. So now our test is correct, but we want to determine a color and blend between three different colors on the three different vertices. So we're going to define V0 as red, V1 is green, and V2 is blue. Let's define those up here. And we're going to define these as floating point because all the math we're doing is in float, and then we'll convert to integer colors at the end. Something like that. Now we need a coordinate system that's going to give us a blended value in between the three vertices. And for that we use barycentric coordinates. So this is a coordinate system where, based on a point inside the triangle, we get three numbers. And these three numbers add up to 1. And they have the property that when you're on a corner, we have a 1 and zeros in the other spot, in the other positions. So this one's 1, 0, 0, this one's 0, 1, 0, and this one's 0, 0, 1. And then on the inside, we can use these to do a weighted sum of the colors on the three corners. So the way we calculate barycentric coordinates is we look at these three subtriangles that this point divides the triangle up into. And each of these is just a normalized area. So we take the total area of the triangle and we divide it by the area of a subtriangle. And that's relative to the triangle opposite of a corner. So for the first component, we're looking at this triangle. So that's why it's 1 here. And as we approach this edge, it becomes 0. And it's negative if we're on the other side of the edge, but we're only going to be testing points inside the triangle that we already know are inside. And so we just repeat that for the three corners. And the good thing is that we already have these areas because these are just the determinants that we've calculated here. So we just need to divide these by the total area of the triangle. To be precise, these are actually double the area because the determinant calculates the area of a parallelogram, but that's a double the area of the triangle if we imagine an edge across here. The determinants just double that, and if we're taking the ratio between two areas, that 2 will cancel out, so we don't need to actually take the areas of the triangles, we just take the areas of the parallelograms. So in here, let's do determinant. And for the whole triangle, we're going to go x1 minus x0, y1 minus y0, and then x2, y2. And then in here, we'll divide them by the total area. And then the red component is just going to be red 0 times bary 0. We just do the weighted sum like this. And that gives us a number between 0 and 1. So we need to scale it up. And we add 1/2 to round to the nearest integer once this gets truncated. And so we'll do the same for green and blue. So let's see what that does. That looks good, but it's not quite correct because we were saying that red was here, green was here. And so that's because for V0, we want to look at the triangle here, which involves V1 and V2. And here, just the naming was off. So we need to change these where D0 is going to involve these two triangles. D1 is going to involve these two, and then D2 will involve these two. And there's our hello triangle. So going from here, there's a lot you could do. You could start interpolating different attributes across the triangle. You could use multiple triangles to create 2D or 3D objects. But that's the starting point, and hopefully the math was clear enough that you could try writing this yourself. So that's it for today, and I'll see you in the next one.